Welcome to 2.3, Rate of Change. This is where we're going to pull some real-world applications into the use of the gradient or derivative function, f prime of x. And we're going to show how it measures the rate of change of a function f with respect to x. An example would be if c represents the value of a car measured on a day-to-day basis, we can say that c is a function of time, where c equals f of t. Therefore, the derivative, or dc over dt, that we can call f prime of t, represents the rate at which the value of the car is changing with respect to the passage of time. If s represents the distance measured from a fixed point to a moving object, then s is a function of time because as time changes, that distance will change. S equals f of t. Then ds over dt, or f prime of t, would represent the change of distance with respect to the passage of time. And the change in distance with respect to time is known as the velocity of the object at that given time t. Let's do some examples. Example 1. The volume of water in a container, or V centimeters cubed, is given by the formula V equals 300 plus 2t minus t squared, where t is the time measured in seconds. So what does the derivative, what does dv over dt represent? Well, it represents the change in the volume of water in a container with respect to the passage of time in seconds. All right, so then what units are we going to use for dv over dt? Volume is measured in centimeters cubed, and time is measured in seconds. So volume on top, centimeters cubed, over, time is on bottom, seconds, or centimeters cubed per second. Another way that we can write this is centimeters cubed, and then we pull seconds out of the denominator by making the exponent on it negative. Since that exponent is 1, it is s to the negative 1. All right, let's find the value of the derivative when t equals 3. I'm going to find v prime, or dv over dt, up here in my original function. I start with 300. Well, n is 0, so even though a is 300, 0 times 300 is 0, and indeed the whole term would be 0. So we just leave that off. Then we have 2t. N is 1, a is 2. 1 times 2 is 2. And then t to the n minus 1, 1 minus 1, would be t to the 0, which equals 1. And as we said, 2 times 1 is 2. Moving over here, my n is 2. My a is negative 1. 2 times negative 1 is negative 2. And then t to the n minus 1, 2 minus 1, is just t to the 1, so I'm just going to write t. Now I'll evaluate that when t is 3. 2 minus 2 times 3. Okay, well I know that 2 times 3 is 6, so 2 minus 6 is negative 4, and that is in centimeters cubed per second. All right. So what does that answer tell us? Well, the value is negative, so it tells us that water is leaving the container at a rate of 4 cubic centimeters per second. So a negative rate of change here tells us that the volume is decreasing. All right, let's try another one. A company mines copper, where the mass of copper, X, is measured in thousands of tons. The company's profit, P, measured in millions of dollars, depends on the amount of copper mined. The profit is given by the function P of X equals 2.3x minus 0.05x squared minus 12. So first, we're being asked to find P of 0 and P of 6 and interpret these results. All right. P of 0 is equal to, if I plug 0 in there, that's 0. If I plug 0 in here, that's 0. So the only thing left is negative 12. P of 0 is negative 12. Now, for P of 6, I'm going to plug in 6 everywhere that I have an X. So in my calculator, I'm going to type 2.3 times 6 minus 0.05 times 6 squared minus 12. And I find that P of 6 is 0. All right, so what do these results mean? Well, P of 0 equaling negative 12 represents a loss of $12 million. We've lost that money because the number is negative. P of 6 equaling 0 represents basically breaking even. No loss, but no profit. All right. Now we're going to find the derivative of P with respect to X and talk about what that represents. All right. The derivative of P with respect to X, you could also write this as P prime equals, all right, N is 1, A is 2.3, so 2.3, and X to the 1 minus 1 is 1, so we multiply that by 2.3, and that's just our constant in our gradient function. Next, we have 2 as N times A, which is negative 0.05. Negative 0.05 multiplied by 2 is negative 0.1. And then negative 12, let's finish this. X to the n minus 1 is x to the 2 minus 1, which is just x to the 1. And then negative 12 is a constant, which will turn out as 0. So here we go. That is my gradient function. And it's going to represent the change in profit with respect to how much copper is mined. All right, so now let's find the value of P and the derivative of P with respect to X when X is 20 and when X is 25. Okay, so when X equals 20, let's find P of 20. So I'm going to plug 20 in to my original function. 2.3 times 20 minus 0.05 times 20 squared minus 12. And I get 14. Okay, now P of 25 all right, let's plug 25 into our original equation. 2.3 times 25 minus 0.05 times 25 squared minus 12, and I get 14.25. Okay, so both there are representing profits, 14 million and 14.25 million. Now, let's go ahead and evaluate the derivative. I'm going to call it P prime of 20. And for that, I'm going to be plugging 20 in here to the derivative or gradient function. And that is 2.3 minus 0.1 times 20. And my answer is 0.3. Okay, now we need to find P prime of 25. Plugging that into my gradient function, 2.3 minus 0.1 times 25, and I get negative 0.2. Okay, so what does that mean? What is the interpretation that we can give here? Well, for P20 and P25, there is a profit, right? X equals 20 has a profit of 14 million, and X equals 25 has a profit of 14.25 million. But what does the rest of it mean? Well, remember, we said rate of change. The rate of change at P prime 20 is positive, so profit is increasing. If we mine more, we will make more money. However, the rate of change at P prime of 25 is negative. So profit at this point is decreasing. If we mine more, we will be losing profit. Okay, so let's find the value then where the derivative is equal to 0. All right, so that derivative, 2.3 minus 0.1x, that's what we found up here, is equal to 0. All right, I'm going to subtract 2.3 from both sides. So negative 0.1x equals negative 2.3. And then I'm going to divide by negative 0.1, and I find that x equals 23. All right, and that is 23, I believe we said 100,000? Thousand. That is 23,000 tons. That would make the rate of change 0. So let's determine profit and interpret the value. So I need P of 23. All right. Going back up to my original function, 2.3 times 23 minus 0.05 times 23 squared minus 12. And I get 14.45. So that's the biggest value I've gotten so far. What does that mean? Well, where the rate of change is 0, moving from increasing to decreasing, we find our maximum profit. In this case, max profit is $14.45 million from mining 23,000 tons. All right. Next, there's a few practice problems. You can absolutely stop the video here and go work them on your own, or you can work them along with me. All right. The area A of a pool of water forming under a leaking pipe is A equals 4t plus t squared centimeters squared after t seconds. So what is the area of the pool initially? Initially would be when time is 0. So at 0, well, let's see. 4 times 0 is 0. 0 squared is 0. So initially, at 0 centimeters squared, we didn't have a pool of water. So this might be when the pipe started leaking. Well, what about after 5 seconds? What about when t equals 5? I'm looking for A of 5. So I'm going to plug 5 into our initial function. So in my calculator, I'm going to do 4 times 5 plus 5 squared. That comes from right here, 4t, but t is 5, and then 5 squared. And that is 45 square centimeters. After 5 seconds, this pool is 45 square centimeters. So what does the derivative represent? It represents the change in the area of the pool with respect to the passage of time. So let's find the value of dA over dt when t equals 5. All right, well, first I need to find dA over dt, or A prime. All right, n is 1, A is 4. 1 times 4 is 4. And t to the 1 minus 1 is t to the 0, which is just 1. 4 times 1 is 1. And then n is 2, A is 1. So 2 times 1 is 2. And t to the 2 minus 1 is just t to the 1. Let's evaluate at t equals 5. 4 plus 2 times 5 equals, well, that's 4 plus 10, and that is 14 centimeters squared per second. So let's use those answers to explain what is happening to the area of the pool. Well, my rate of change is positive, so the pool is expanding. And so here it's at 45 square centimeters, and it's expanding at t equals 5 at a rate of 14 square centimeters per second. So our best interpretation is to say, at this time, t equals 5, the area of the pool is 45 square centimeters, and it is expanding at a rate of 14 square centimeters per second. And that's at this exact time, t equals 5. All right. Next, the weight of oil in a storage tank W varies according to the formula W equals 5t squared plus 640 over t plus 40, where W is measured in tons and t is time in hours. Before I do anything, I'm rewriting this. W equals 5t squared plus 640 t to the negative 1 plus 40. All right, Let's find the weight of oil in the tank at T equals 1. Okay, so I'm going to do 5 times 1 squared plus 640 times 1 to the negative 1 plus 40. I get 685 tons. So that's W of 1 equals 685 tons. Okay, let's find the derivative. dW over dt, or W prime, is equal to N is 2, A is 5, 2 times 5 is 10, and T to the 2 minus 1 is just 1, so we'll have 10T. All right, N is negative 1, A is 640. Negative 1 times 640 is negative 640. And then T to the negative 1 minus 1 is T to the negative 2. 40 is our constant. We know it'll be 0, so that just goes away. So now we're going to find the rate of change of the weight of oil in the tank when T is 3 and T is 5. So W prime of 3 equals, we're just going to plug that straight into here. 10 times 3 minus 640 times 3 to the negative 2. All right, and I get a decimal, and that is negative 41.1 repeating. I know that 0.1 repeating is 1/9, so I have negative 41 and 1/9. That's negative. And we'll answer this down here in D, but remember it's negative, so at that point, oil is going out of the tank. Now here, W prime of 5. So let's take 5 and plug that in. 10 times 5 minus 640 times 5 to the negative 2. And we get 24.4. I know that 0.4 is 2/5. So 24 and 2/5. So the only thing missing here now are my units. Now I know that this is going to be ton per what? Well, T is my time in hours, so it's H negative 1. So here I'm losing oil at a rate of 41 and 1/9 tons per hour. But at 5, I am gaining oil, or the weight of oil is increasing at a rate of 24 and 2/5 tons per hour. All right, so let's write that out. At T equals 3, we are losing oil at a rate of 41 and 1/9 tons per hour. And at T equals 5, we are gaining oil at a rate of 24 and 2/5 tons per hour. So now let's find the value of T for which the derivative is 0. All right. So I'm going to take my derivative and set it equal to 0. So I'm going to write it out. 10t minus, I'm going to rewrite this back into fraction form, 640 over t squared equals 0. Now from there, I'm going to add 640 over t squared to both sides. So that's 10t equals 640 over t squared. Now I'm going to multiply both sides by t squared, which leaves me with 10 t times t squared is t cubed equals 640 I'll then divide both sides by 10 to get t cubed equals 64. And then I'll take the cube root of both sides to find that t equals 4. So the rate of change is 0 when t equals 4. All right, so what does that mean? What is our interpretation here? Well, at t equals 4, let me write that better, the oil in the tank stops decreasing and will then start increasing. So at t equals 4, we have the minimum, because it stops decreasing and then starts increasing, so we have a minimum allowable rate of oil in the tank. All right, great job. Join me next time for 2.4, where we're going to look at local extrema and optimization. Have a good one.